Hi everyone, my name is Jenny, and today I'll be talking about a recent project we worked on to incorporate contextual signals in recommendations at Pinterest. So I'm sure many of you already know what Pinterest is about. Maybe you know it as that site with lots of pretty pictures, similar to maybe Tumblr or Instagram. Or perhaps you think of it as that app people use to plan their weddings, which is a very common and valid use case. But at its core, Pinterest is a platform for discovering new ideas. Our goal is to help people find and save things that they love. On Pinterest, there are a few main surface areas for this kind of discovery, so let me show you what I'm talking about. One of these surfaces is the home feed, a personalized feed of content curated for each user. We take into account the user's recent activity on Pinterest to inform our system. We select the most relevant pins that we think you're interested in right now and show them to you all in one place. Each item in the feed is called a pin, and as you can see here, the user is being recommended pins for their interests in home decor, fashion, recipes, and more. Another surface for discovery is the search feed. Here we show you a more specific set of recommendations. We recommend pins that match a textual search query that you provide. You can see here that the user searched for nail designs, so we're showing them the most popular nail design pins. Sometimes users are looking for something even more specific than their original search query, but they don't have the right words on the first try. So we provide machine-learned search guides, which you can see at the top row here, and you can click on them to add to your search query and help narrow down what you're looking for. Today we're going to be focusing on a recommendation source at Pinterest called related pins. In the product, related pins are shown when a user clicks on a pin from any feed. So users can arrive at related pins from a variety of sources, including home feed, search, or even another related pins feed. Let's say for this example that we clicked on the golden retriever pin. When a user clicks on the pin, they're brought to a more detailed view, which we call the pin close-up. Here you can see a bigger version of the original image, plus a description, maybe user comments, and the link that it came from. Underneath, you'll see the more like this section, which is one of the places where related pins are most prominently featured. So scrolling down, you'll see a feed full of content relevant to that pin close-up. These related pins give users a chance to discover highly relevant content to the pin close-up they were interested in already. And they can explore similar pins here. As you might expect, these recommendations are very engaging for our users. Related pins actually powers 40% of engagement on Pinterest. Let me give you a quick overview of how this works under the hood. So, as you can see, related pins is an item-to-item recommender system. We generate candidates using a variety of techniques. A main one that we use is collaborative filtering, in which we leverage our data about which pins are often saved together. So if users tend to save pin A with pin B, we know that they're likely to be related, and we'll recommend them as related pins candidates for each other. Another main approach is using historical engagement data. So for a particular close-up pin, which related pins did users most commonly click on? It's like a voting system through which we know which related pins are likely to be the best candidates. We also have a machine-learned model to rank the candidate pins. In ranking, we care about both how relevant a candidate pin is to the close-up, as well as how engaging it's likely to be to the user. So we use features based on both the visual and text signals of the pin, as well as engagement data of the pin. So now, given a close-up like the one on the left, we can generate a feed of results that are generally relevant and engaging. You can see that the style and color scheme of all the outfits in the results are pretty relevant to the close-up pin. This is a good user experience for a large number of cases, but depending on the context of the pin close-up, the user could have vastly different intents. Some users may have come to the close-up pin from casual browsing, such as their home feed. So just checking out different pins that catch their eye, and they're not looking for anything in particular, just general inspiration. In this case, those related pins results would be great. Meanwhile, other users may have closed up on that pin through a search query for a very specific set of results. They might be looking to buy a pink trench coat, or maybe they already have one and are looking for outfit ideas for the day. At Pinterest, we realized that making recommendations solely on aggregated engagement and relevance data was not enough. By taking the user's context into account, we could better predict their intent and get them more quickly to the results that they're looking for. In particular, we know that users coming from search have executed a specific text query and clicked on one of the pins in the search results. This context tells us that the user has high intent and is interested in something related to both the search query as well as the clicked pin. These related pins results we saw earlier would have made sense for the casual browser, but given the search context, we can see that half of the top result pins are not relevant to the user search query of pink trench coat. To improve related pins for users coming from search, we decided to first add a new set of candidates specific to both the search query and the close-up pin. This helps us move away from relying solely on collaborative filtering and historical engagement data for candidates. So how do we find candidates that are both relevant to the query and the pin? Our first version of hybrid search candidates involved rewriting the original search query. We took the top annotations from the close-up pin and added them to the search query. So pin annotations are generated based on things like the pin's title, description, link page, and other signals. For example, perhaps the top annotation for the close-up pin we were just looking at was street style. We'd add that to the search query and rewrite it to be pink trench coat street style, and perform a new search request with the rewritten query. We can return these results as additional candidates for related pins. And these candidates successfully combine the user intent from search query and close-up pin. However, we realized that we could improve it even further. So for our V2, we not only rewrite the search query, but we also changed the way that we score the candidates. At Pinterest, we developed a custom embedding that captures both user engagement and content-based features for each pin. So content-based meaning things like visual, textual types of features. We fetch this embedding for each of our search candidates and calculate their similarity to the close-up pin's embedding. And by scoring the search candidates using this embedding distance, we're able to return candidates that are most relevant to the close-up pin. Adding hybrid search candidates performed well in our experiment, but we calculated the cost of shipping it to all users and found that it would double the current search QPS in cost. Since every time a user closes up on a search result, we're performing a search request to fetch candidates for the related pins. To scale it, we built a smaller search index with only the best pins. These are pins that are popular, meaning they have high engagement. They're not stale, meaning they had impressions in the past 7 days. And they're also strongly tied to search queries. So they're part of our memorized high-quality search model. In addition to this, we also reduced the number of pins going through full scoring on the search backend to help save on cost as well. These modifications helped us reduce our total cost to 10% of the original cost, which made it possible to ship hybrid search candidates to all users. Now that we have these hybrid search candidates, we combine them with the original related pins candidates and pass them to our original re-ranker. This gives each of the candidates a score according to their relevance to the close-up pin and their engagement potential, as we had discussed earlier on. Since the ranking scores only reflect the candidate's relevance to the query pin, we added another layer on top that takes search query into account. This layer boosts candidates based on the original search query. For the boosting layer, we first tokenize the search query and then compare the tokens of the annotations to the annotations of each query candidate pin. So based on how many matches there are between the tokenized search query and the candidate pin annotations, we boost the ranking scores of these candidates. We did this in order to make sure that candidate pins that match both the close-up pin and the search query get ranked to the top. Finally, we output the hybrid search related pins results. So these final results include the new search candidates, ranked with original related pins candidates, and boosted on candidates that match the search query. As you can see in this final example, The top results are now tailored to both the close-up pin and the search query. Compared to before, where half of the top results did not contain a pink trench coat, all of the top results now contain a pink trench coat. For a user with focused intent, this provides a much better user experience. These gains were reflected in our experiment metrics as well, where we saw that user engagement for related pins coming from search improved by 20%. This shows us how impactful it is to take user context into account when generating recommendations. As a next step, we'd like to move away from boosting based on the search query match. Instead, we'd like to add search query match as a feature in our model so that it can more intelligently determine the importance of this feature in the final score. We also hope to continue to improve related pins further by understanding and incorporating more context into our recommender system. One of the contexts we found promising is user context across different categories on Pinterest. For some categories, such as fashion, users might be looking for a more diverse set of results for general inspiration, whereas for a category like recipes, we found that users are often looking for very similar related pins. They want recipes that match the same type of dietary restrictions or even ingredients that they have. A lot of users have a set of ingredients and are only looking to make recipes that incorporate them. So there's still a lot to be done here to improve the related pins experience across Pinterest for different intents and contexts. From this project, we learned that incorporating user context can significantly impact user engagement with our recommendations. Taking context into account in candidate generation can help us fetch the most relevant content to what a user is looking for. In addition to that, using contextual signals during ranking and boosting can help us surface the best candidates. Especially for a versatile recommender system like related pins, context helps us better understand the user's intent and make better recommendations for every use case. Thanks so much for listening to my talk, especially to the Pinterest related pins and search teams for their support, and also RecSys for giving me this opportunity.
Yeah, I have one question about the, can you go back to the few slides on the diagram on the ranking and the candidate generation? So I have a question on that slide.
This one?
Go back. Thank you.
Which one?
I think the screen may be frozen or I don't know, freeze.
Sorry.
Anyway, yeah, actually I took some notes.
Okay.
So there's one component called ranking with ML models. I'm just curious. Oh yeah, this slide. When you say rank with ML model, so what is the objective of this ML model? Just curious about this part.
What is the objective of the ML model?
Yeah, so what is the response you use or label?
Good question. Yeah, so for our ML model, our main objective is around engagement. So we have several engagement signals that we use, including clicks, saves, close-ups, and long clicks. So those would be our main objective, although we've also added in several other objectives for product reasons as well.
I see. So let's say you have like multiple objectives, but are you training multiple models, each model for one objective, or how do you combine objectives together?
Yeah, so our model is actually a gradient-boosted decision tree, and we're able to combine all of these objectives into a singular objective using this type of model. So we only train one model, basically, instead of training separate models, like you mentioned.
Okay. Yes. My second question is actually the next step. When you said like you boost a candidate that match the search context, so it's like you are training a different machine learning model, or is this like a heuristic based like boosting?
So your question is, how do we generate candidates based on different contexts?
No, the second step is after you rank with ML model, right? The next step is you boost the candidates.
Boosting the candidates.
When you say that boosting, are you use another machine learning model to re-rank?
So right now our boosting is not based on an ML model. We hope in the future to incorporate an ML model into this step as well. But right now the boosting is just based on heuristics. So if a candidate pin has, let's say, 3 matches with tokens of the search query, we'll incorporate that as like into like a heuristic function, which will produce a boosted score for that candidate.
I see.
Yeah.
All right, thank you.
Thanks. Yeah.
It seemed like you may have partially answered this question, but what method do you use to rewrite the search query?
Right.
Like, I'm assuming you're comparing the selected pin to the original query, and then seeing what else could be added to it. Yeah.
So the question is, what do we use to rewrite the search query? So currently, we look at the top annotations of the candidate pin, of the close-up pin, and we add some of those top annotations with some processing to the search query, and it's rewritten that way. So some things we look at are like, are any of the annotation terms duplicates of the terms in the search query? And if there are, then we try to select those annotations at a higher priority. But we try to like remove the duplicate terms in the meantime. And we also have tried, different variants of this hybrid search query rewrite. We found that actually the simpler rewrites perform better because sometimes when we add too many annotations to the end of the search query, it becomes less coherent to our search model. So it becomes a search query that a regular user wouldn't necessarily execute. So then the results that we find for those are not as high quality as the simpler types of rewrites.
Thanks.
Yeah.
Hi, great talk. Very interesting, and I like the example of a pin code. So my question is that with this method, it seems like the results are very focused and very relevant. But what do you do for diversity for related pin since it's more discovery oriented? So in the same pin code example, what if people want to see what purses or shoes go with it? So that's my question.
That's a great question. So diversity in related pins is kind of a tough topic because we want to show pins that are relevant enough that users are interested in them, but also give them some room to pivot, especially on categories like fashion, where they might be looking to complete an outfit or something like that. We have several different approaches that we've used to try to incorporate diversity. One of them is by incorporating what we call basically like blending in some ratio of results that are not re-ranked with the rest of the results. So our current machine learning model is based on engagement, but also heavily focused on relevance. So a lot of these more diverse results might not rank as well with our model. So we'll incorporate some pins from other sources that we force blend essentially into the results to try to get signal on whether users like to see that in the results of related pins. I think we're also constantly improving our candidate generation, looking for new candidate generation sources that surface not only the engaged candidates we've seen already, but also darker content that users might be interested in, but might not be currently in the collaborative filtering or memorized historical engagement models. And another experiment we're looking to run is in our candidate generation step using collaborative filtering, we actually have a parameter that we can tune there. So those are the candidates where we see pin A and pin B are often saved together. So then we'll recommend pin B for pin A as a related pin. We can expand the random walk that we perform to generate these candidates to include more hops of the types of pins that users are saving together. It's kind of like a very high-level explanation, but essentially we can, increase the breadth of that random walk in order to include some more diverse examples in those candidates as well. Yeah.
Thanks.
Thanks. Awesome.
Hi.
Hi.
Diogo from Farfetch. I really like your idea. I think it makes a lot of sense. But why did you choose to do a boosting candidate of the search query test and not incorporate it directly in the machine learning model and now trying to incorporate it
Good question. So the reason why we started off with boosting is because as an industry company, we want to move quickly and try to test out our ideas as efficiently as possible. And boosting was the way that we saw that would get us to the end goal of showing these hybrid search results at the top of the feed without dealing with model understanding, things like that. Because it was possible that we could train a new model that incorporated these features, but that the model wouldn't fully understand the idea of this search query match yet. So that's why we are listing that as a more future direction or longer term solution so that we have more time to figure out the exact types of features we need to really replicate this kind of boosting in the model itself.
Yeah, that makes total sense
Yeah.
because the cost of trying a feature just for the sake of let's see if it works, it's
Yeah.
really high if you incorporate it in the model directly. So my question is, did you have done that before? That means, did you try already some boosting with some other features, and now the model that you are using, it's using already some feature that you had boosted in the past, for example? Or it's the first time you tried this boosting thing?
Oh, like have we tried other boosting features in the model before?
Yeah, because
Uh-huh.
now I see this as a framework. So you want to see if a feature is
Got it.
relevant enough. You
Yeah.
use a boost, and then it's relevant. Let's incorporate it in the model. And now we have a new model, and now we have to try a new feature. And again, this process, do you see it as a framework, or is something?
I see.
Just
Yeah, so maybe if we have a lot of types of content that we want to boost in the future, this might not be as efficient of a way to go through the boosting and then adding the feature every time. So we've had a few other examples where we've done something similar, where we had some boosting before adding these features to the model. But in general, I would say that this is not a common use case for our system. So maybe it's okay to do this occasionally, this kind of framework. Yeah.
Okay. Thank you.
Okay,
very
thanks.
much.